Hi, everyone. I'm Mark Plagge. I'm a postdoctoral researcher at Sandia Labs, and I'm presenting our work we've been doing entitled Expressive Dendrites in Spiking Networks. And I've been working with Suma Cardwell and Francis Chance on this project, and I'm quite excited to kind of showcase what we've been doing. So my background is in computer science, so I will present this, but with apologies to the neuroscientists, because I'll be possibly a little reductive when talking about dendrites. But dendrites are a fantastic source of computation. Their structure and their communication, and basically they exist as these powerful, nonlinear processing elements. And so we're looking at ways to kind of leverage this computational power in the context of machine learning. I'd like to view them kind of as almost providing a pre-processing step. Basically, the information is transformed while it is transiting through the dendrite. And what's really kind of exciting is that there exists hardware that implements various dendrite computational methods. There's a sub-threshold CMOS-based hardware design that both exists and has nice simulation tools for it. And with this, we can kind of look at dendrites as a compute-on-wire method that is implementable and buildable using standard CMOS techniques. And all of this is great, but we have this kind of problem where we have these really neat possible applications for dendrites in neural networks, in spiking networks, but in order to use that, or even to justify building out new hardware types, you want to have a suite of applications that would leverage this type of hardware. So there's this kind of problem where we could achieve great performance and great efficiency using dendrites in hardware, but we don't really have applications that would leverage it right now. But we're not going to build applications that leverage it right now because, speaking as a software developer, we're lazy, so we like to use easy to use, well-defined application packages to kind of build out our algorithms. So what we're working on is kind of building a easy to use ML-based system that will allow algorithm development using dendrites in a hardware-informed way. And so to that end, we've built this dendrite-enabled spiking library. Leveraging SNN Torch and PyTorch, we abstracted the complex network, the complex dynamics of a dendrite cable, and implemented it in a way that it has parameters that are learnable within PyTorch using a gradient descent type methods. So you can put this into a, say, convolutional neural network, like a ResNet, but it also integrates with SNN Torch, so you can actually attach a LIF neuron to the end of this chain and integrate it into a larger spiking network. The library's basic building block is a one-dimensional chain of dendrites, but you can combine them to kind of create more complex structures. The abstraction is such that you are given a lambda and tau value, and the lambda value is a abstraction of the spatial constant in a dendritic cable. Tau is this temporal constant, which also kind of represents the capacitance and resistance of the circuits. And we also have a leak and a input weight value, which are a drain and gain value on the input signals. So the important thing, though, is that this library needs to be both informative and informed by hardware. So we wanted this to, first off, be able to allow people to generate larger networks with spiking and dendrites, which change or affect or inform the design of hardware of how many taps we need to build on a chain, how much, like what's the maximum capacitance we need, things like that. But we also wanted to be able to constrain the library. So if we knew we needed to build dendrite chains with, say, 6 taps, we could build out the neural network in software with 6 taps and limits on the lambda and tau values that represent the hypothetical hardware limits. And so we can transfer these learned parameters, and our goal is eventually to transfer them to hardware, but we're working on transferring them to hardware simulation tools. And dendrites are surprisingly powerful. As kind of a first example, that little diagram I have of two dendrites talking to each other across tau and lambda attached to a soma is a single neuron with two dendrite inputs. And with just those dendrite inputs and an output soma, you can create what I like to think of as a temporal AND gate. It's a form of a coincidence detection network. And just by tuning one parameter, you can change the sensitivity of these dendrites to the distance and time of the two inputs happening on the network. So you get this great nonlinear computation that adds temporal dynamics to a network. And if it's implemented in hardware, it can be extremely efficient when computing this, as it's doing it as the information travels across the network. Kind of as a better example of what you can do with our dendrite library, we took an example from the SNN torch examples, which is to learn a nonlinear function using a spiking neural network. In this case, we took a couple of spiking neural networks and a dendrite-enabled spiking neural network, and we took two functions, the square root of x and mish of x. And mish of x is a nonlinear activation function. I like mish. I think it's an interesting function, but it's just two arbitrary nonlinear functions. And we collected a set of 1,000 random samples from the function space in between 0 and 4. And we trained these networks for 100 epochs using these functions as our data. The three networks we used two networks that were just leaky integrate and fire neural networks. One of them has a hidden layer consisting of 256 LIF neurons attached to an output neuron, and the other one has 16 LIF neurons in its hidden layer. We expect, and you'll see the 16 LIF neuron does not perform as well as the 256 LIF neuron network. And to compare to these, we created a 16 by 16 dendrite-enabled spiking neural network. And this network is basically 16 neurons, each with 16 dendritic input taps. So the number of inputs to this hidden layer is the same as the 256 hidden LIF neural network, but the number of outputs from that hidden layer to the output LIF neuron is 16. And so we're kind of comparing how much accuracy can we get using dendrites with the same amount of spiking communication as a much smaller LIF network. We allowed it to learn tau and lambda and the leak and gain values, and we kind of limited the maximums of these so that the capacitance wouldn't explode. So these are realistically buildable in hardware in a theoretical hardware sense. And so we trained it on these for 100 epochs. And as expected, in the middle is the 16 LIF only neural network. And this is the mean squared error when running against these functions. And the 256 LIF network was significantly better, which is also to be expected. But we found that the 16 dendrite LIF neural network was able to perform as well as the 256 LIF neural network. But even though it's only outputting 16 distinct spikes to the LIF output neuron. So we've been able to increase the dynamics of the output neuron without having to increase the number of total communications being sent to that neuron. And this is exciting since one of the biggest bottlenecks in larger scale neural networks is data transfer. There is a huge memory bandwidth problem with large scale LLMs. And this will, in hardware at least, allow much more efficient computation of neural networks since the processing is happening as the data is being transferred from the input to the output. And as we're working on this, I wanted to put in a plug because one of the key components of this library is that we want it to be realistic to implement on a dendritic piece of hardware. And so to that end, we've been working with an intern on a tool called Santa Fe, which actually will have a tutorial on Friday if you're interested. But it's that tutorial will be learning about learning how to implement the Loihi hardware in Santa Fe. But our goal is to also get our dendrites in there so we can have a hardware simulation of a dendritic neural network with LIF neurons. We're also working on implementing this in ML techniques. These dendrites actually perform fairly well in traditional ML applications, adding them to, say, a ResNet, and we're working on applying them in a temporal context in terms of attention networks. Vision transformers are actually a pretty good application for this sort of thing, and also pooling layers. But we're also looking at trying to find other compelling network designs. These dendrites really add a lot of dynamics and kind of capabilities to a spiking neural network or even an ML network. And we're working also on releasing it as an open source tool. We're debating whether it should be an add-on to SNNTorch, and we might have to make a pull request, or if it should just be a standalone library. But either way, it will be released under the Sandia Labs GitHub page. So, keep your eyes open for a Dendrite library appearing there. Yeah, thank you.